on Monday we looked at for top of function templates and how we have type names and we have templated types and functions, and we looked at for min function in quite a bit of detail. And looking at that min function, we end up with about a half-hour discussion actually on what happens if we have different types being mixed in and stuff like that. And so for second half of Monday's lecture, kind of went off on a bit of a side tangent, which is okay. But what we're going to do today is we're going to continue to pick up whereabouts we got distracted from Monday. And so what we're going to look at is the idea of name resolution and how templates are deduced at compile time. And so when we're thinking about a function template, there's the designer of the function template, and there's the client or the user of the function template. And so there's a two-step process in how these names resolve. There's the type-independent names, okay, which are resolved at the definition of the template, okay, and the designer provides the declaration. So that's where we have we already know the data types basically at this point. For type-dependent names are resolved at a point of instantiation. So that's the big T and a big U and things like that when we have a template. And if there's multiple points of instantiation, the compiler chooses one of these as the point of instantiation for the template. Okay? And we're going to explain what this actually means in the next couple of slides. As we highlighted on Monday, you need to place all your template definitions and declarations in header files. Okay? So, again, thinking about assignment 3, the only thing that you're required to submit for assignment 3 is actually your .h file. Because the entire set of templated declarations and definitions go in the .h file. This is a special rule that applies to templates. Okay? So, if we take a look on the left-hand side at this slide on name resolution, we have a set of code here which, first of all, at the top, it defines a function. It's a normal function called print. And this print function takes in a char star and outputs it to an IO stream. We then have the definition of a template function. And then below that we have, and maybe this is sitting up in .h file by the way, below this we have some client code. And the client code also has a definition of a print function, which also takes it, well, this one takes in an int and prints it out, okay? And so in this code, we've got two normal print functions that are overloaded. We have a templated min function, and in the client code, we call min. When we're thinking about how this thing compiles, what happens is the compiler comes down the .h file to start with and sees this normal function here, and it compiles it. It then sees the templated function here and doesn't compile it. The templated functions don't get compiled like normal functions get compiled. Okay, so the print function gets fully compiled. The min function doesn't. It gets declared in memory, so the compiler knows that there's a min function that's templated but doesn't define it at this point. It then goes into the client code, and this print function here, the second print function, it gets compiled perfectly fine. And then it's not until the next line where this min function gets actually called that it goes, oh yes, I have a template, I have a recipe for how this thing needs to be built, and it goes back and compiles an instance or instantiation of this template for whatever types are being passed in. In this case, they're being passed in ints, so it substitutes t for int everywhere through here. So int min, int a, int b. And then what it does is it goes, okay, so print the minimum of these two values. Okay, that's a char star, so this print up the top gets called. And then int c is equal to the result of that expression, print c. Now c is now an int. And so this function down here gets called. Now this is different to if this wasn't a templated function, and if this was just a normal function called min that took in ints. This actually wouldn't compile in this order, actually wouldn't compile at all if this was a normal function, because this print that's referred to inside this function isn't actually defined or declared until it gets into the client code. Can we see how this is different? So this min function actually requires a function that isn't actually defined until it gets inside the client code. If we compiled this like a normal compiler would go and compile if it wasn't a templated function, this wouldn't compile because the second min function hadn't been declared. Okay? So the name resolution and the compile process for templates happens when they're instantiated, when they first get called. Okay? So it can make the code a little bit confusing to read, because normally when you look at the code, you read it top down. Normally in C, you read the code top down. With the templates, that's not strictly how you do it. You go find the point at which it's instantiated and work backwards from there. Okay? Now, still on that slide for 1 second. Even though this template here took in an int, there's nowhere in this slide that we actually explicitly said, create for int version. It worked out to create an int version based on the arguments going in, which were ints. And so this idea is template argument deduction. Okay? Now there's two types of template parameters, and again we looked at this on Monday. There is the template parameters, which is the type name stuff up the top, okay, and those can be types or non-types, okay. For types is for T, for non-type. We looked at, for example, on Monday with size, and we took an int regarding the size. The call parameters are the standard bits that go into the rest of the function prototype. Actually, if I bring back up Monday's slides, if I just quickly go find the code, I'll show you what I mean. Okay, so on Monday we had, up on the right-hand side, this find min function. This top line here, this is the template parameters. The second line in here, these are the call parameters, okay? But they're related to each other. Okay? And so template argument deduction is the process of determining the types, okay, so the types of the type parameters, and the value of the non-parameter types from the function arguments. Okay? And so the function, and the return type is ignored. We don't introduce the return type at this point. Now, this is important for function templates. So it's automatic deduction of what the type required for these functions only works on function templates. It doesn't work on class templates. And we'll look at class templates on Monday. But on class templates, you have to be explicit in the type of the thing that you're defining. So if I look at the code on the right-hand side, we've already seen this with a vector. We can't say vector v equals, and we're going to just initialize it with some doubles like this. We can't do that and have it deduce that, oh, that's going to be a vector of doubles. For a class template, we have to be explicit and say the word double into there, and that's what we've been doing all semester. Okay? But with find min, so if I say find min, or like that, 1, 2, okay, this is deducted or deduced to be of type int. I don't have to say, I can, but I don't have to say explicitly this is the int version. Okay, so this is what we're talking about in terms of deduction. Okay, the compiler is automatically working out what the types going in are. Yeah.
Could you put in find min int, comma 4, and then say the sizes for that? See how you put in the where the cursor is now.
Oops, wrong computer.
Yeah.
So you want me to put in int, comma 4?
Yeah, so that's not saying the size is 4.
Yeah. So this isn't going to exactly compile for this code, okay? example. Okay, so this is a slightly different example, but this is what we're looking at in terms of a deduction of what's going on. Okay, yep. So if we take this apart a little bit more, here's how it breaks down. Okay, this is kind of what I just showed you. Okay, so the type parameter is this t on this top line. The call parameters are the actual variable names on the second line of it. Okay, and so if you say min12, it deduces to be int, min, and int. If you say 1.1, 2.2, it deduces to be double going in there. The return type is irrelevant. What this means is if I say int I is equal to min12, it's still going to be int min min for a function. If I say double I is equal to min12, it's still going to return an int that then gets promoted to a double, because putting this double over here means nothing. Okay, it's all about what's going into these call parameters that deduces it. Okay. Here's the example that I just messed up on the right-hand side. Okay, but this is the same example as from Monday. This is about we've got for type and non-type parameters, and so the top line we have unknown type t. We also have a known type, which is this int for the size. And then the call parameters are dependent on these types. Okay? And we had this example on Monday with arrays. Okay, so far this is all just revision from Monday, just with a little bit more explanation of what these things are actually doing. Now, with function templates, there's limited conversion for different type arguments. If I was defining a normal function, and its normal function took in a double, and I gave it an int, it would just get cast automatically. This doesn't work like this for template functions. There's very strict limited rules for conversions. Okay, the conversions are these. There's, pardon me, there's L value transformation. Okay, so there's L value transformation in the sense that you might have a function that takes in a pointer. And if you remember, an array, so a standard old-fashioned C-style array, is actually a pointer itself. So you can convert automatically an array to a pointer, because they're kind of the same type. Okay? So you can do an L value transformation like that. You can do the const conversion, so you can pass in something that's non-const into a const function, and it works. Yeah. And if you're looking at class inheritance, which we haven't looked at, we're not looking at inheritance until about week 10 or 11. Okay, but if you're looking at inheritance, if you have a derived class, so a class that's inherited from a base class, you can pass that derived class into a function that accepts the base class. And because it's polymorphic, it will behave as if it was a base class. Again, we'll look at that a whole lot more when we get to object-oriented programming. Okay, so there's no promotion of ints to doubles and doubles to ints and things like that that you'd normally expect for functions. If you have a function that takes in a type t, and you instantiate an int version of it, and on the next line down you instantiate a double version of it, you've got two overloaded functions. Okay? And we're going to talk more about these in the coming slides. Now, again, this is what we spent about half an hour talking about on Monday. We're about, say if we have the template for min, that takes in 1.0, which is a double, and 2, which is an int. This is a compile time error. The reason why it's a compile time error is because the min template that we're looking at, I'll see if I can find it again, the min template that we're looking at on Monday just had the single type name, the single version of t. And so t, in the first instance, is a double, and then suddenly you're saying, well, t in the second instance is an int, and it doesn't work. And so on Monday, looking at the right-hand screen, we put in type t and type u in order for this to work. Okay? but it's just still stuck on a version that's just got T sitting there. In order to get this to compile with an int and a double, if we still wanted just the int version to work, we'd either have to static cast for D, so the double down to an int, or we'd need to actually put the explicit type in, so min int ID, and that means it's now going to explicitly sort it out for you. Or if we wanted the double version, we have to static cast for double through to, static cast for int through to a double, or the same on line 5 down here on the bottom of the slide. On the bottom of the slide, give it the explicit type at that point. Yep.
So if you explicitly instantiate a templated function,
Yep.
It doesn't create new ones if it finds like one that you haven't explicitly instantiated. It tries to use the ones that you haven't.
Oh no. If you explicit, so the question is this: if you explicitly instantiate, does that prevent it instantiating other versions? No, it will happily go and instantiate other versions for you.
But it will now if it finds a good match.
No. The reason why you've got the ints here is this is an explicit call to instantiate the int version and then pass these versions up to this int version. If on the next line down, I just said min again without giving that int like that, it again wouldn't compile. Okay? So it's explicit for that line and that line only. Okay?
So this is different from, like this is explicitly instantiating the int version with those parameters, but you can also explicitly instantiate a template function at the bottom of the CPP file, right? And you can it will create those up front.
Okay, so what we saw, so this is whereabouts we're getting confused with Monday. So what we saw on Monday is the explicit instantiation inside the template file, which is different to this. Okay, so this is being instantiated when it comes into code and actually being called. Okay, the explicit instantiation that we saw on Monday, okay, is still explicit instantiation but slightly different. That wasn't a call. That was a, hey, go and generate this version regardless of if there's a call to it or not a call to it. Okay, that's why it isn't recommended. It's better to do it this way. But the reason why we're showing you that on Monday is if you wanted to, you can force it to do that. Okay. And the reason for showing you that on Monday is if you really wanted to actually define a template, but then despite defining a template, still limiting who can actually use your template, that's how you can achieve that sort of behavior. Okay, because you can define the template and then still limit it off to certain type values depending on how your code is structured.
Right, and in that case, it won't make other.
It depends where the template is defined. So if the template is defined in the header file, it will still go off and make other versions. Do you remember the version on Monday that we looked at, the template was actually defined in the .cpp file. Okay? So it depends where it's defined. But general rule, define your templates in header files and don't explicitly generate them like we saw on Monday. Okay, so that example on Monday was why not to do these things and the problems that you can get into with doing that. Okay. If you need to do it this way, this is the way you should be doing it. Okay. Now, this does continue to lead into Monday afternoon's discussion though, which is, say we want to take in two different types. So say we want to take in an int and a double. And this is going to switch from talking about min, but talking to the sum. Okay? So say we want a function called sum that's going to sum or add up two types. And so we might want to sum for int 3 and belong 4. Okay? And say we want to do that in reverse. So 3 becomes belong and 4 becomes the int. In this case, in both situations, we want this to return belong. Okay, because belong is the best data type for this. Okay? But even if we put T and U here to pick up these two different data types, we don't know what our return type is going to be. Because in the first instance here, the higher value, for long, was the second parameter passed in, so the u, and in the second example, for first parameter, so the t, was the one passed in. And remember with function overloading, we overload based on call parameters. Return types mean nothing about function overloading. So you can't define two versions of sum that both take in int and long and then return a different type based on the same call argument. So it doesn't work, it doesn't compile. Function overloading only works based on the call parameters, not for return type. So before C++11, you would have to actually define a third type name to explicitly tell it what the return type that you want it to be was. So you'd have to go type name T1, T2, T3, and then onto the front of sum you can say it returns T1 and it takes in a returns a T1, takes in a T2 and takes in a T3. Okay, if the T1, T2 and T3 are confusing you can call them T, U and X or something like that. Okay, these are just three different types. And so you would explicitly have to say this returns a long. Okay? Now this was for pre-C++11 way of doing it. Does anyone remember from Monday how we solved this problem? Auto and decal type. So here's the same thing done in C++11. We've got T and U. Okay? I don't know why the screen's going all fuzzy. I apologise. So we've back to two type names. We've taken T and U, and the decal type is able to work out what the type is going to be. I was going to switch this to use both projectors to see if that's going to improve. Oh, what have we done?
Maybe you can put your code on that one.
Yeah, but no, the lecture recording's gonna. Yeah, I've got to keep that one up for lecture recording. Oh, now everything's locked up. Now it's back. Okay, seems to be working okay. Okay, I'll switch back to the code if need be. Okay, so if we look at this, we have the auto and the trading return type working and the decal type working out what the type of these things are going to be. The way in which this decal type works, okay, is it's saying just generate me a default version of T and generate me a default version of U, add them together, and whatever the return type of that summation is, that's what you should be returning. Okay? So in this case, an int plus a long is a long. A long plus an int is long. So it always works out that it needs to be a long. Now, of course, that requires the addition to be defined, so that overloaded addition symbol to be defined for those types. So those types need to know that there's an overloaded addition that takes in that particular version. Again, think back to assignment 2 with the Euclidean vector. One of the things you had to define was the multiplication symbol. And multiplication symbol for the Euclidean vector, there was a couple of different versions of it. One version of Euclidean vector just multiplied against another Euclidean vector. And it returned, if I remember correctly, I think it returned a Euclidean vector. If it didn't, it returned a double or something like that. But anyway, for Euclidean vector times the Euclidean vector resulted in some type. Okay, actually it might not have returned a Euclidean vector. I think that returns a double, yeah. Okay, so Euclidean vector times Euclidean vector returns a double. Euclidean vector times int, I believe it was, otherwise it might have been times a double. Can't remember now. Okay, but anyway, Euclidean vector times this different data type returned a Euclidean vector. And so see how we have multiplication symbol overloaded, and there was different return types. This decal type, in exactly the same way, if we're doing this with Euclidean vectors, would deduce which version needs to be called and give us the correct return type. Okay? Everyone clear on this? So if we actually go and break down Monday's example, okay? So Monday's example, we had this piece of code. So we wanted to deduce what the return type of min was going to be. And I was surprised, and I think most of you were. You guys were either surprised at my reaction or you're surprised that this actually worked. but you're surprised that we could deduce this because we have no way of normally knowing what this min is actually going to be if it's two different types. We can't work it out, and this isn't the same as adding example whereabouts we could explicitly say it was going to be a long or an int or something like that. Because if we did, if we were able to explicitly tell it what the type is going to be before we passed it in, well, we might well not have passed it in anyway because we're going to already know. So this expression version of decal type is actually a particular, really quite advanced version. And on the next slide, I'll have a link at the bottom that you can go read that goes into a lot of detail about how it works and how it deduces the type. Because I was puzzled by this. I was surprised that it worked, but I'm not joking. On Monday afternoon, I went and spent about 3 or 4 hours trying to understand why. Why did this work? How does it work? Okay? Now, I don't strictly expect you to go spend 3 or 4 hours working out exactly why, but you should have the idea this isn't magic, that there is logic and stuff behind the scenes of how this thing's working. Okay? So, I've got a bit of a quiz, a bit of a question for you. Is if I have min and it takes an int and a double, so this is exactly the same as what we had on Monday, we had it taking an int and a double, and the same situation but reversed, it takes in a double and an int, then what is the return type? Is the return type of these two functions, both cases a double, both cases an int, or in one of the cases it's an int and one of the cases is a double based on the values that are being passed in? What do people think? Okay, because this is exactly what I wrestled with on Monday, because I didn't know. Okay, I know the answer now, but I didn't know at the time. So what do people think?
It depends.
You think it depends? Okay. So who thinks it's always going to return a double? Sean's cheating. Who always thinks it's going to return an int? And who thinks it depends? Okay, I thought it depends, and I got it completely wrong. Now, the reason why I got it completely wrong is remember that functions aren't overloaded by return type. We cannot overload a function by return type. And the template has to be constructed at compile time. The values going in go in at runtime. Okay? So it has to figure out a way to always actually know what the return type is. And so it deduces like this. The first part of that decal type for A less than B part, okay? So how does the expression A less than B work if A is an int and B is a double? How does it work? Okay, so it converts them to the same type and then compares them. Okay, so in the case of comparing an int and a double, the int is going to be promoted to the double. Okay, because it's better to automatically promote upwards instead of promoting downwards. You try to avoid narrowing. So you do not want to promote, or not promote, you don't want to narrow for double down to an int, so instead the int gets promoted up to a double. And this doesn't just work for doubles, this works for a lot of types. Okay, so there's automatic type promotion that goes on. So for expression, A less than B will automatically promote one of the types up to the other version of the type. Okay? And so this automatic promotion becomes this temporary thing. And we've talked about L values, we've talked about R values. There was a slide I deliberately didn't tell you on Monday because I thought it was too confusing. There's another thing called X values, which are expiring values. There's yet another value type called a PR value, which I'm not going to go into detail on. Again, you can read about. But a PR value is a pure R value. It's a pure temporary explicit value, okay? And so this A is promoted to one of these temporary double values, okay? And so therefore, when you get into the second part of this expression, okay, so you get past for A less than B, and you get to the return type where it's returning either A or B, this A is now this pure R value. It's this pure temporary double type. Okay? So regardless of whether A or B is returned, the return type is always a double. Okay? Do you understand the logic of what's going on there, of how it's deduced it? Okay, so we passed in an int, we passed in a double. In order to do for comparison, it had to promote the int to a double. Therefore, it had two doubles. Either was going to return one of those doubles or return the other double. Therefore, it always returns the double. Okay, there is a very, very, very long article on the links there that you can go read later on if you're confused by that. And probably if you read that, you'll be more confused. But if you're interested in how the compiler actually deduces that stuff, it is actually quite fascinating. Yeah.
What if you were to give the decal type a function that would return different types depending on the values of
Okay, so the question is, what would happen if you gave decal type a function that returns, wait, what?
So it will actually return a different type depending on...
You can't have a function that returns a different type.
You can't do it.
No, there's no function that returns a different type. A function always has to have a fixed return type. So decal type is always going to work out what the return type of things are. You can give decal type, tell it, go work out what the return type of the other function is, but that function is always going to have a fixed return type. You cannot have a function that returns something that arbitrarily changes. Remember, we don't overload on function return types, we overload on the call parameters. Okay? This is all to do with type safety, and this is well beyond my knowledge of these things. There's all courses you can do on compilers. Actually, there's a whole course you can do on compilers that will go into a lot more detail about how these things work.
What if you say like A is equal to 1, question mark, A, B? Because then if B is a double, B never actually gets promoted.
So the question is, if I put in the expression A is equal to 1, question mark, A colon B. So B never gets called. You'd probably have to go compile it yourself and see what happens. Okay, I definitely don't have time now. I can sit down with you later on today and take a look at it if you wanted to. I wouldn't be able to tell you if it returns an int or a double, but my feeling is it will return always one of those two, and you might have to play with it to find out.
Or maybe it will just won't accept that.
It might not accept that either. Yeah. Okay, so we've got about 12 minutes to go, so I'm going to try to rush through some of these slides. But what we're getting into now, we're actually going to be looking at in the tutorials for next week. So we're going to look at a thing to do with specialization of templates. Okay? And so let's take a look first of all at string literals. If I have this fixed strings, CSE in speech marks, and comp 4001, which is actually the old course code for this course, in speech marks, I've got two different types at that point. One is a const char size 4, and one is a const char size 9, okay? But for backwards compatibility with C, the string literal is actually assigned to a const char star, okay? So these things can be compared. So I have a function or program here, okay, which works out for min. This is the same template we've been dealing with all week, okay? And so I have, okay, I've changed it from CSE, but I've got ZYX and I've got ABC. And so what do people think the output of this function is? I'm calling min on these 2 pointers. Do people think it won't compile because they're different types? Remember that, actually these ones actually are the same type, so if these were different lengths, they're different types. Do people think that this won't compile? If I've got to give them the game away, it will compile. Okay, so what do people think the output of this is going to be, this min? Is it going to say ABC is the min or ZYX is the min? Or I'm going to give a third or fourth case, you don't know, is for next one. You don't know what order it's going to print out in. I'm not going to get you to answer it because I've talked to you about it before. Okay?
Have you?
Yes.
Yes?
Yeah, I talked about an hour ago with you about this exact problem.
This?
Yeah, about this. Yep.
So it's going to do it on the pointer values,
It's going to do it on pointer values.
and I suspect that they go, I actually don't know whether or not they go backwards.
They don't go backwards. So it's going to do it on pointer values. Okay?
Oh,
And so the pointer values, see, I have talked to you an hour ago about it. It's going to do it on the pointer values, and the star S is defined before star T. So in most situations, Z, Y, X will get printed out. But actually you don't know, because you don't actually know whereabouts in memory these are going to be assigned. You could end up with one assigned in one piece of memory and the second one actually assigned in an earlier piece of memory. So the short version is we've got a problem at this point. This min function works on normal types, but does not work on pointer types. So how can we specialize a template to work especially on pointer types? Okay? Well, we can by using what's called template specialization, which means that we can create this extra template that comes after the normal template definition that doesn't have any type names go into it. So template, just open square, angled brackets like that. The return type is char star. In this case, it's just been type def. The function name's the same, so it's still min. It takes in this explicit type. Okay, so this const char star has just been type def to PCC, which I assume stands for pointer const char. Okay, so this is an explicit version of min that takes in these two types. And in this case, because it's old-fashioned C-style string, it's doing a string comp, and therefore it works. Okay, so we've provided a specialized version to make this work. Okay, so we've got a normal template that works for all the normal cases, and this is an edge case, so we've provided a specialized template for this edge case. Okay, and so the way in which you might organize this in terms of your function is in your .h file, you have a definition of your normal function, and then below that you have your specialization. Your specialization has to come after your normal definition. Now what you can also do is if you want to, with the specialization, you can put the specialization inside a .cpp file rather than the .h file. Okay? So if you know the .h file has a definition of something and you think it's wrong, you can provide your own special overloaded specialized version of it inside your .cpp file. Okay? But you've got to be careful about putting that in your own CPP file, because if you are compiling multiple objects from lots of different CPP files, then you have to put that specialization in every single one of them. Hence why it should go in the .h file. Okay? But again, it depends on the circumstance. So we're going to look at specialization in the tutorial next week. Let's look very quickly at function template overloading. So I've got a program here that has a normal template, a specialization template, and a normal function. All three of these functions are called min. The template is the same one that we've seen all week. The specialization is for char star, what we've just seen. And we've got, for some bizarre reason, just a double one, just already built for us. Okay? Now, there's particular rules in which things get preferred or things get called. Okay? But the way in which things get preferred or the way in which things get called is the preference is to go to the ordinary normal function first. The second preference is to go to specialization. And then in the worst case, you go to the template. And so what you're trying to do is you're trying to go most closely defined first and then work out to the least defined. So we've got 4 function calls here. Call to min with value 1 and 2. 1 and 2 are ints. We go up and we go, what's a double? And that's a char star, so we just got to go to this normal template. And so we instantiate this normal template for an int at this point. Okay, so we've got int version. We go at 1.1 and 2.2. We go up and we go, oops, there's a double version of that. Okay, so the ordinary function gets called. The next line, 1 colon 2.2. One of those things is an int, one of those things is a double. This template up the top isn't going to work because it is assuming that both things are the same. The char star, of course, isn't going to work because it's not a char star. So therefore, the min function taking the double, the 1 gets quoted for double there, and that normal double function gets called. Then on the final line, S and T, which are, again, constant stars, they call the specialized version of the template. Again, I'm going a little bit quick through this because this is what we're going to be looking at in the tutorial next week. Yeah.
What's the point of even declaring the template of the const chart?
What's the point of the template for the const chart? Is exactly what you just saw in the previous slides. If we don't define that template const star,
yeah. No, but then why don't you just...
it's going to always get you the wrong order.
No, but why don't you just, like, because you have to actually declare it,
Yep.
Why even use the template at all? Why not just declare it as...
Oh, why don't you just declare it as a normal function?
Yeah.
Because we're showing you an example of specialization.
So just because you can.
Just because you can. I mean, like, it might not be the best example, but in this case, it's weird.
Do that?
Why would you want to do that?
When would you want to actually do that?
When you need to do that.
But will you ever?
Yeah. Yeah, there'll be. There's actually a case next week that you'll see again in the. Wait for the tutorials next week. Okay. Okay, so I'm really rushing because I've got 4 minutes to go. There's also default arguments that you can give templates, and again, we're going to revisit some of these things in the next few weeks. So we can have, here we go, we can have this example whereabouts we have a template, okay, again for min, and we can take in a predicate which says, how do we compare these things? And so the predicate just says use standard less, which is for less than operator. But in the case that we've got strings, we can pass in a string comparison in order to do it correctly. Okay? And there's some code there you can take a look at to see how it works. And there's also a lambda function further down that you can take a look at how that works. So you can pass in no comparison, you can pass in a function pointer, or you can pass in the lambda function and make this template work on all 3 of these things. Okay? I'm going to come back to this one in a couple of weeks' time because this one is not in next week's tube, at least not at the moment. Finally, real quick, and again we're going to come back and talk about variadic templates in a few weeks' time. But variadic templates, the best way you can think of them is working a bit like how printf works. So we want a function called print that takes in a whole wide variety of arguments. And so we have this version called print. It just takes in one type and prints it off to the screen. Okay, this is kind of how printf works, kind of. We've got an overloaded function template, okay, print, that takes in 2 types, but see these dots on the end of it? This thing makes it a variadic template, which means that inside the second print function, we say print head, which goes off and calls this first one, and we say print tail ... which will recursively call this second function again and again and again. Kind of. I'll wave my hands a little bit. And so on the first line, we're about to call print 1 and 2.0f. Okay, I've got an int and a double. It goes off, prints the head through that version, calls for tail, which is now a double, creates a second version of print that takes in a double. The third line, or the second call to print, int double string. It creates an int version of print, a double version of print, and a string version of print. And actually, because of a variadic template, on the next line, you actually see there's about 5 different versions that are compiled. And so you don't see this code, but that template there actually gets expanded at compile time out to about 5 different functions like that. And so you've got the const char version, okay, which is for the strings. You have the float version, you have the int version, and that variadic template gets compiled into a float and it char style version, and an int and a float, and a char style version. Okay, so it's a way of expanding and being able to handle multiple unknown lengths of templates. We're going to return to that in a couple of weeks' time. I am out of time, so I'm going to stop now. Next week we're looking at class templates. Next week's tutorials is looking more in detail over specialization and variant templates.